So it's a pleasure to introduce Professor Stefano Pirandola. He is at Department of Computer Science, University of York, UK, and works in the field of quantum information. If you follow the field of quantum information, you must have his review articles. He has written a lot of review articles in quantum sensing, quantum communication, satellite-based quantum communication. So you can't if you follow the field, you must be knowing his name. Anyway, I will give a formal introduction about Professor Pirandola. He did his MSc from University of Rome, La Sapienza, in 2001, and then did his PhD from University of Camerino, Italy, in 2005. And then he was there for 2 years doing postdoc, then moved as a Marie Curie outgoing international fellow to MIT, and 7 to 9 he was there at MIT. Then he came to York as a Marie Curie fellow, and spending 2 years there, he joined as lecturer at York. And since then, he has been there and became full professor in 2016. So he started to work on quantum cryptography and quantum networks since he was a fellow at MIT. He has contributed to the development of the continuous variable formulation of quantum information, which has natural implementations in quantum optics. In particular, his main interests are in the areas of quantum communication, cryptography, and sensing, for which he has established ultimate theoretical limits, besides designing practical technological implementation. So here is Professor Pirandola. I think he must be talking about quantum communication, but since title is not there, I don't know what topic he's going to talk about. Anyway, welcome to Professor Pirandola.
Okay, thank you very much. Thank you very much, Ravindra, for the introduction. Okay, I'm going to share the. I mean, it's a pleasure to talk with the school, and I'm going to share my screen. Okay, so let me see if you can. Okay, so first of all, can you see the screen? Can you see?
We can see, yeah, very clear, and we can hear.
Okay.
Also, yeah, you can.
Good. Okay, so part it's full screen. Okay, so I'm so happy. I'm happy to talk here. And yes, the topic here of this presentation is near-term quantum safe networks. So quantum networks is a very big name. Well, I mean, it's a big umbrella name because there are many different types of quantum networks in general, depending on the task. And well, I will start quite generally, but then I'm going to talk specifically about quantum cryptography. So the application of quantum cryptography in networks. So these are the outline of the talk. So I'm going to start with talk a little bit about quantum internet. What is like this ecosystem, and then I will go to quantum safe communications, right? And when I talk quantum safe communications, is particularly I mean quantum key distribution, QKD. Yes, here I will discuss different security levels that we have in QKD today, and corresponding different types of QKD repeaters that we can devise, and correspondingly different types of architectures for QKD networks. So it's kind of going from the security level up to increasing the complexity into, let's say, channel repeaters and then networks. And specifically, I want to stress about near-term developments. So something which is done already and is going to be done. In the very next probably 2-3 years, or even less, from the point of view of quantum safe communications. And this actually these near-term developments are connected with this idea of effective QKD repeaters that I will describe, and I will finish with some take-home messages. Okay, so let me start with the very general picture, quantum internet. So this kind of full stack that goes from different levels. So you can see that the very first levels, let me say, the level 0, level 1, that the very basic fundamental steps are about security. Okay, so I also put like post-quantum crypto as like somehow zero-level security. Yeah, zero-level security because well, I mean it's a technology that is going to be certainly integrated with quantum cryptography. So it's going to be part of this this quantum internet picture. And of course, I mean QKD, so quantum cryptography for links and networks. This is a very important building block here in the quantum internet. But then we have also, I mean, other steps like this classical quantum cloud. So already today, we have some quantum processors which are accessible via the internet. And so this is already quite well developed at the moment. And clearly the level 3, 4, and 5 are the most difficult, especially the creation of efficient repeaters that allow to have distillation and distribution entanglement between remote stations. So this is very important for creating like very I mean, a very strong and robust quantum internet infrastructure. Quantum interfaces also, I mean, there are different type of technologies that needs to be interfaces, different types of frequencies. So this is also a very important area, which is very difficult, especially when we look at the microwave to optical transducers. So the possibility to somehow convert optical qubits into microwave qubits for, I mean, processing in superconducting computers. So this is a very important area as well. So when you put all this stuff together, then we can really achieve the quantum cloud, where it's not just quantum computers, but there are quantum computers that are connected with quantum communication. So you can do teleportation from one quantum computer to another. You can interface quantum memories. So you have basically the entire picture of a quantum internet where different technologies are interfaced together, and you can do quantum information processing, you can do quantum communication, and also you can do quantum storage. Yeah, so that's actually clearly more difficult. That's more in the area of quantum computing. I'm not going to talk about this part today. I'm going to talk about the security part, but I wanted to mention this. And again, I wanted to mention about this hybrid structure that we have at this top level. Again, with different technologies. I mean, again, we have to interface these three main areas: quantum communication, quantum processing, quantum storage. And together with Sam and my colleague Sam, we discussed a little bit of this challenge back in 2016, how you can well do that, and I mean, what are the challenges behind this kind of big construction of the quantum internet. But let's talk about security QKD, which is what I mean. I'm more interested now at the moment, and clearly it's very the near-term application of quantum networks. So when you talk about QKD and quantum encryption in general, first of all, I wanted to make sure that we understand that there are different levels of security. So I mean, we have like a very somehow entry point, which is the standard QKD. So what is standard QKD here? I mean the QKD protocols that guarantee channel security. So somehow, I mean, you have like Alice and Bob, which are remote stations, and they are connected by a channel that can be a fiber. And so QKD is going to encrypt the information in such a way that attacks that I mean, they in such a way that we are, I mean, Alice and Bob are somehow okay with respect to attacks that are basically against the channel, the fiber. Okay, so what's in the middle? That is very the standard and the first type of QKD that's been developed, and a lot of BBRT4 and I mean all these protocols. And clearly here, we're also sub-levels of security. So this kind of channel security can be developed at different levels. I mean, it can be like, depending on the types of attacks, depending on the type of security, it can be asymptotic, composable. So these are, I mean, an entire zoology already here with behind this channel security. Now, the next step here is the measurement device independent QKD and more recently twin field QKD. So now this kind of security is a bit higher than the standard security because you are also adding security not just with respect to the channel, so the middle fiber, if you want, between Alice and Bob, but also from the point of view of the receiver. And typically, these are schemes which are based on a middle third party. And so Alice and Bob, they are not connected directly by a channel, but they have two different channels. And these channels, they connect them to a middle relay. And this relay can be, is making a measurement. Usually, I mean, for MDI is a balance state measurement. In twin field is a more complicated measurement. But this measurement can also be done by potentially by the eavesdropper. So somehow the Alice and Bob are able to extract the key, even though the eavesdropper is attacking the channels and the measurement device. And they can do that because, I mean, they can somehow apply some checks. I mean, they can collect statistics. They can anyway check what the relay is doing. And thanks to these checks, they can also understand what type of power simplification, what type of procedure they need to do in order to extract the key. So the bottom line is that this type of security is higher because it also make the receiver, which is in this case the central relay, completely secure. So it can be even operated by the eavesdropper. And finally, there is the device-independent QKD, which is the higher level. It's based on entanglement. And in this case, not just the receiver, but also the sender can be attacked by the eavesdropper. So somehow there are these kind of side channel attacks, so-called side channel attacks, which are attacks which are not against just the quantum communication channel, but also against the setups. Okay, so this level of security is the highest. Is going to be okay also with respect to these side channel attacks. So even if the setups are somehow compromised for both the sender and the receiver, I mean, the parties are able to extract a key. Now, this is very, very cool, very, very, very important. But so we are increasing security from bottom to top, but also increasing cost. Clearly, because you go from something that doesn't need any entanglement to something that actually needs entanglement, and also decreasing the rate. So the bottom one is very easy to implement. I mean, it's easy to implement. The intermediate one is a bit more difficult, but can be implemented. The top one is not really practical at the moment. I mean, having like, well, I mean, you can implement certainly entanglement sources. That's easy. The point is that the rate is very low. So you don't have bright entanglement sources. So these type of protocols are very low. Their rate, their secret key rate is going to be not realistic and not good for realistic implementation in technology. So these are more about like future developments at the moment. So standard QKD basically standard state of the art. MDI already and twin field already from the experimental point of view, but they need some further development. DI QKD certainly is implemented experimentally, but is not that technologically viable at the moment. So that's basically the situation. So channel security, receiver security, and sender security going from bottom to top. But from the point of view of the rate, we have a problem because the rate level is high for QKD. Standard QKD is somehow intermediate for this kind of protocols and becomes low or very low for DI QKD. Okay, so that was like a very big picture. And let's talk about the standard QKD, so channel security. So we have many protocols here developed. So it's a situation where Alice and Bob have a direct channel between them, like a fiber or free space link. And here we have two general categories, two general families of protocols. This is called discrete variable protocols, so DVQKD. So what is a discrete variable? Because they use discrete degrees of freedom to encode information. So for example, I don't know, the polarization qubit. I don't know if you consider like polarization of the optical field, you can encode a qubit. So that's basically a bidimensional Hilbert space or things like that. So we have a lot of protocols there, BD84, B92, and so on. So continuous variable QKD has a bigger space. So it uses continuous variable degrees of freedom. So it's going to use like a quadratures of the quadratures of the electromagnetic field. So like the position momentum, like the equivalent of the position momentum of a particle. So when you do that, you don't have just, I mean, a bidimensional Hilbert space, but you have an infinite dimensional Hilbert space. So the bottom line is that with QIQT, without going to many details, you can encode a lot of information into the systems, into the quantum systems. And for this reason, you can potentially reach higher rates than standard DV-QKD. But at the same time, they're not so robust like DV-QKD for long distances. So one has to find like a compromise with in terms of rate and distance, in terms of what type of protocols they want to implement. So that's actually the, right. When you have this kind of protocols, you can create this type of trusted repeaters. So suppose, okay, you have like Alice and Bob, and then you have like a chain like this. So Alice, Bob, Alice and Bob. So you can encrypt somehow the channels, but you are not really secure with respect to the parties, okay? But if you assume that the parties are trusted, so if you have a main to check, I mean, a method to check that, I mean, these Alices and Bobs here are not somehow attacked by an eavesdropper, or they're not impersonated by an eavesdropper. So in that case, if for this kind of trusted nodes, trusted repeaters, trusted nodes, so what you can do, you can use this kind of directly this kind of protocols. Okay, so what you do like a session here with for example BB84, another session here BB84, another session here, and then basically what you do, you create a key between these two parties, another key between these two parties, another key between these two parties, and then the middle parties, they use a one-time pad to compose, somehow swap the keys to the other parties. So this Bob here in the middle can do like key swapping basically, and it can swap a key, it can generate a key between these two Alices, and then this Alice using another key with this Bob can create and swap the key between the first Alice and the first Bob. So that's actually, I mean, a very standard way to swap keys using one-time pad in a chain. And at the end of the day, I mean, the first Alice and the last Bob, they can share a key. Now, the second part is here. I mean, I'm going up into this level of security. And what we have MDI and twin field. So I was mentioning at the beginning, in the case of MDI and twin field, you don't have a direct channel, but Alice and Bob, they connect to a middle relay. So what they do, they send systems, okay, to this middle relay. This middle relay is going to do some kind of measurement, and then the measurement, the outcomes of the measurement are communicated back to the parties. And using these outcomes, Alice and Bob can create correlations between their local variables. So it's kind of a posteriori creation of secret correlations between Alice and Bob. And this type of scheme works even if the middle node here is operated by an eavesdropper. Now, there are many protocols. Now, we started with MDI in 2020. That was 2012, if I remember well. And then, okay, also with CVMDI after a couple of years, I think. And then we had like twin field very recently, and all these other protocols. Now, what's happening here? When you have this kind of structure, you have an untrusted measurement-based relay. So the one in the middle is generally untrusted. It's generally untrusted means that, I mean, it's secure even though it can be operated by an eavesdropper. And so that's very important. So there is no entanglement. That's also very important, because, I mean, Alice and Bob are just sending states with not entangled states to the middle relay, which is doing like a measurement, usually a bell-like measurement for MDI. It's a single hop architecture. So one of the problems here is that this architecture by itself is not scalable. So you can do that with a single hop. Single hop means that, I mean, there's just a single relay in the middle. So if you want like a multiple hop, then you need to mix this kind of strategy with a different strategy. And I mean, the key rates are good. I mean, they're not very high, but I mean, they're good. And if you consider the twin field variant, so if this relay in the middle is not just MDI, but it's twin field. So let me see if I can actually use like a laser point. Okay, so if you use like a twin field node, you can reach very long distances. And it's actually very feasible architecture for near-term networks. Indeed, I mean, this type of repeater, untrusted repeaters for QKD with no entanglement, Boson and twin field nodes are currently being developed by several groups. And these are going to be like a very, very big thing, in my opinion, in near-term quantum safe networks. Okay, so finally we have like device-independent QKD. And yes, here we have basically the variance of the Eckert protocol proven in 91, where you have like a middle relay where it's basically an EPR node. So it's a station, a distributing entanglement to Alice and Bob. Well, I mean, no, I mean, Einstein, Podolsky, Rosen correlations. And okay, because of this entanglement is distributed between Alice and Bob. So Alice and Bob, they can do like they can check somehow. They can do they can do basically some checks on this entanglement distributed, and so they can basically so they can basically create some checks of like a no locality checks to exclude the possibility that the outcomes from their local measurements are correlated with an eavesdropper. So they can always be sure that what they get measuring this entangled state, what they get is not correlated with any eavesdropper. Okay, here there is, I mean, the reason is because, I mean, they can exploit this monogamy of entanglement. So if they reach a very high level of correlations, such a way to violate the Bell inequalities, though they're completely sure that, I mean, the entanglement is ruled out from the picture. And clearly now this kind of situation is kind of with the type of a node here, you can create an untrusted entanglement-based repeater. So again, it's like a repeater, which can be even, I mean, can be operated by the eavesdropper because it doesn't matter. I mean, as long as they can check the correlations that they're going to get from this state. It's clearly based on entanglement, is a multi-hop architecture. I mean, generally this can be scaled. So you can have like, I don't know, another entanglement base. So you can have like multiple hops here. But clearly you need to increase the sources of entanglement. It's the problem with this is that the key rates practically now are quite low. So they're not competitive with any, I mean, any type of classical infrastructure we have now. So I mean, the key rates are really extremely low. So this is a very, very long-term solution. So it's not really feasible for near-term quantum safe networks. And it's going to be like a use case for future quantum computing networks, because at the moment where you are able to distribute entanglement so efficiently, actually you are at the level where you are built somehow quantum internet already, and you can create a distributed quantum computing environment. So the ability to send, to distill and distribute entanglement in an efficient way is equivalent to have multiple quantum computers interconnected on a quantum internet. So that's why this is a very kind of a long-term architecture. When this architecture is there, basically, where quantum computer would be already operating, and would be, or I mean, they will be interconnected. So I mean, certainly security has to be fixed before this. So that's why this is not a near-term quantum safe solution. Right. So let me give you like another big picture of what's happening with the QKD networks then. Okay, so we have different approaches. So we have the standard QKD, we have MDI and twin field, and then we have device independent. And okay, with different level of security, different type of way to build repeaters. And well, when I say repeaters, I talked about QKD repeaters in general. Okay, and the top level here, there would be entanglement distribution repeaters. Okay, so different ways in which you can build repeaters, and then a different way which you can build also networks. Now let's start from the bottom. So we really see that, I mean, with the standard QKD, you have like a trusted nodes. You can build trusted chains. So in general, you can also build trusted QKD networks with more complex topologies. And the level of security is point to point, meaning that you are really encrypting the channels between two trusted nodes. So it's like between one point and another. So security is in the middle. And that's really state of the art because it's very feasible, it's currently implemented. So for instance, that's like what you can have in a trusted QKD network. So you may have like a situation like this. So you may have like a local area network. I don't know, this could be like a university, I don't know, a department network with some, I mean, trusted switch, and then users connected with that switch. And then you may have another department, or I mean, different branches of, I don't know, a bank, whatever. And then so you have this trusted LAN. Maybe they're trusted because they're based on this kind of protocols. And then in the middle, you need to use repeaters in the middle if this somehow this distance is going to be non-trivial. Now, in this type of architecture, the trusted QKD network, the repeater is a trusted node. So it's something that you need to trust, okay, with some way, somewhere. And then you can do that trick that this trusted switch can distill, have a key with this trusted repeater. This trusted repeater has another key with that one, and then trusted repeater can swap, okay, the keys in such a way to connect that switch with that switch. And then in turn, these switches can have keys with these local users. So this actually, so links are secure. Each link here is secure, but the hubs, the switches and the relay repeaters has to be trusted in this architecture. This is what we have now. There've been several actually networks have been created with this type of idea. In China, Europe, UK, also in the US. Now the next step is let's go a bit higher in terms of level of security. Let's try to implement a little bit of MDI and twin field in the network. So if you do that, so you combine standard QKD and MDI twin field. So you have like a kind of a hybrid architecture where you have trusted LANs, so you may use somehow standard QKD for your local area network, but then probably you want to use untrusted, you want to use MDI and twin field for the repeaters. Because the repeaters are outside your somehow circle of trust, okay? So you may have like a local area network, which is okay to be trusted because say under your control. There's another local area network, which is trusted because it's under your control. But then what's in the middle, they could be like a hope, like outside your organization, and you want that to be probably based on MDI and twin field, because you don't care if it's a trusted or not. Okay, it can be generally can be untrusted. So that's why you may combine this kind of approaches. So you have like this type of inter-LAN security, where now if eavesdropper is attacking between the two LANs, it's okay, you're fine. Even if it is attacking the repeater, because the repeater is untrusted. And that's also, near term. And now this type of technology is going to be developed now, like a very, very, very first steps we can see today with experiments. And they're not very well developed already. This actually, I would say, is going to be near term. And current and near term in the next couple of years, we'll see a lot about this. And that's actually could be like the idea. So you have like a trusted local area network, again, with like before, like with a trusted switch and users connected with that. So having here is based on trusted QKD. But then you have another trusted LAN, But when you have in the middle, then the repeater, the relay that you have in the middle is in this architecture is based on MDI or twin field. And this means that even if it is attacked by an eavesdropper, you can still have security. And this is inter-LAN security, because security between that LAN and that LAN. Okay, finally, okay, we go to the top, and we got a mix between, let's say, MDI and NDI. So you can create like something that, I mean, I will show you like in the example, which is actually end-to-end. So it's really just Alice and Bob and two very remote parts of the network. They can be secure about communication. And this feasibility is long-term because it's based on entanglement. So you may have something like this, okay? So now you have a LAN, local LAN network. It's not based on a trusted switch. It's based on an untrusted switch. It could be, for instance, an MDI switch. So you have like, I don't know, like an MDI measurement here. So two users, I mean, many users connected with this MDI node. For instance, these two users they can communicate by communicating with this node, right? But then what's happening with, I mean, that user and that user, so they need to be connected, and he can use like an entanglement-based repeater. So a station which is sending entanglement here and entanglement there. And one doing that is kind of collapsing, is kind of, connecting that MDI with that MDI node. And this create, and now this user can be connected with that user through these MDI measurements. So the idea is that like you have MDI measurements in the local area networks, but then you have repeaters at the outside of your local area networks, which distribute entanglement between the different LANs, right? So you see, you have an inter-LAN entanglement distribution by these repeaters. And within the repeaters, if you do, within the local area networks, if you do MDI, what you're doing is basically entanglement swapping, okay? So that's exactly the idea. So that's a very a powerful architecture. And it's secure with respect to the links, it's secure with respect to the switches and also with respect to the repeaters, okay? So again, this is sending entanglement there, and then the MDI at this work, what does the MDI is doing entanglement swapping. Okay, so you can swap entanglement between in such a way that this user is entangled with that user there, or whatever, or I mean everyone else. I mean, or this can be entangled with that one, so and so on. So it can be operated to distribute entanglement on I mean between the very different, very remote users. And that's clearly powerful, but it's the problem is to devise this kind of repeaters, entanglement distribution repeaters, which currently cannot really achieve high rates. So okay, let me check a second. Okay, about 25 minutes. Right? Okay, so this is actually the whole picture. So I would tell you that okay, so the bottom part here is current state of the art. I mean, the top level is a long term. It's probably comparable with the development of a full quantum internet or nearly there. And the next step is this one. And so the creation of this type of networks with this type of inter-LAN security. So something like this, okay? That's actually what I was thinking. So like local networks which are trusted, but then the repeaters here in the middle are based on MDI twin field, okay? So because of that, you have, I mean, the disruptor is attacking these repeaters, you're fine. Right, so there's a very big question here now. I mean, if you go in, I want to go into details of this because actually this is a very important architecture, which is, again, I mean, developed at the moment and will be developed in the next couple of years and so on. So let's see, we say MDI twin field. We want to be more precise about this type of repeater, QIQT repeater in the middle. So what type of repeaters do we use actually here? So we actually use MDI or twin field, okay? So we have to make a choice. It depends on the situation, okay? So it depends on the distance between, for instance, this LAN and this LAN here, okay? It depends on the distance. So I mean, as a general rule of thumb, you have that MDI is a simple choice for short distances. So if the distance is not so much, so probably you want to use MDI because MDI is simpler to implement with respect to twin field. But also you say probably you want to use MDI only if there is some kind of switching to do here at this level of the repeater, which is not present here, for instance. So I'll show you what I mean by switching here. Otherwise, if the distance between two LANs is big, then you want to use twin field, because twin field then is an effective repeater. So it's actually able to repeat, to increase the key rate with respect to just the direct transmission between these two local area networks. So let me tell you what I mean by the user. So okay, use MDI. So one MDI has to be used in this kind of architecture. So again, this the architecture. So you have LAN A, LAN B, LAN C. These are my trusted LANs, and then I have like my MDI and a repeater here. And okay, now you see here, there's a short link between these two LANs. So probably for a short link, you don't even want to use MDI because you just want to use like a direct communication. Okay, here the links are short. Well, you can use I mean, what we can use here, you can use MDI as basically as a switch. Okay, so I don't know, the local area network A wants to communicate with B or C, and MDI is basically creating the connection depending on the demand. Okay, so so the MDI, depending if you want to connect with B, MDI is going to work between, I mean, A and B. If you want to connect with A, so MDI is working with A. Sorry, if you want to connect with C, the MDI is working between A and C. So if these are short links, you can certainly put an MDI. So I got actually a raise hand. I don't know if I need to answer now or later. Do interrupt?
You can continue, Professor Pirandola. We can ask questions. We can tackle question at the end. Yeah.
Okay, good. Not just because I see there is a raise hand, so probably I will reply later then. Okay, so actually MDI is not. So why you want to use as a switch? Because it's actually, to be honest, is not an effective repeater. So does not be the direct communication. So if you actually can go for a direct communication, it's better to do that and use MDI. MDI is we know now that it's good for. It's not good for somehow. It's not really a repeater. So it's maybe used as a switch. It's different when you have like a long links. So if you have like something like this, that LAN A, and there's a long link and a long link here. So if these links are long, then well, probably this maybe become too long for direct communication. So your key rate could be 0. But if you put like a twin field node, you can actually increase the key rate. You have like a positive key rate. So using a twin field here, twin field node not only can be used as a switch, in terms that you can decide to go from A to B or from A to C, for instance, but also as an actual repeater. So some device that is actually able to increase the key rate. And that's actually the most important application for twin field. So to cut it short, what we have, I mean, we can use this kind of switches in the middle. It can be MDI or twin field, but I mean specifically, twin field is going to be the best choice for long links because it's going to be a repeater, something that is going to help within this kind of network architectures when you have long distances. And clearly, I mean, it's not just twin field. I mean, there's many protocols that have been developed after this, and they're going to be simpler and simpler probably to be implemented. So that's actually a very hot area now in quantum cryptography. So let me tell you about now a little bit more into why MDI is not good and twin field is good, and why twin field is an effective QKD repeater. Okay, so what do we mean? Which is but what we mean by being able to beat the direct communication, okay, between these two LANs, okay? Okay, so to understand this, now let's just, take, let's talk about what are the limits of the quantum communications, okay? So suppose that, I mean, you have like a link, okay, between Alice and Bob, like a fiber, and the fiber is a lossy channel. So you have some transmissivity eta for the channel. That means that the 1 minus eta is the fraction of photons that you lose in the environment. Eta is the fraction of photons which survive the channel. And usually for optical fiber, I mean, the eta, the transmissivity is very simple, is simply related, connected with the distance, okay, but the simple formula, I mean, depends on this kind of quality, rate, loss distance factor. But usually it's a very simple formula for that. Related to the distance in kilometers. So the far they are, clearly the more lossy is the channel. And so what is an effective repeater? So an effective repeater is a third party, okay, that is able to help in this scenario. So when you consider this scenario, there will be some kind of optimal performance, okay, for this kind of point-to-point quantum communication. By optimal performance, I mean the best possible key rate that you can do here in this kind of situation. And that is a value, some kind of value, okay, some kind of bound. Now, if I put something in the middle here to help the communication, I want that thing in the middle is going to violate that bound. So it's going to give you a boost, an enhancement with respect to that bound, okay? And that bound, I mean, this is a bound that we developed and we proved in 2017. And so it's called also the PLOB bound, okay? So what is this bound? So whenever the transmissivity eta here between us and Bob, I can easily, with this formula, I can tell you exactly what is the maximum number of key bits, or quantum key distribution bits, so secret bits that you can extract per use of the channel. So I can tell you what is the best rate of QKD, okay? So in particular, that's very simple, okay? If you do like eta, they compute this minus log 2, 1 minus eta, so you get this, now it's a value, and this actually is the ultimate performance of any quantum communication over that lossy channel. So it's actually more general. It's not just for QKD, it's also for entanglement distribution and a qubit transmission, okay? So it's give you that value here, gives you the optimal rate for sending secret bits, okay, over the channel. It gives also the optimal rate for sending entanglement bits and also qubits, okay? So remarkably, is the same value for all this, okay? Specifically, we're more interested in QKD. So this would be the optimal value for sending secret bits through this channel. Now, this actually was proven in 2017, but actually there was like 1 bit of this result was started to be proven in 2009 when I was actually at MIT. So it's a result which is basically on 2 parts, like a lower bound and an upper bound. So the lower bound was proven in 2009, and the upper bound was proven in 2017. And then, okay, since these are matching, you have established exactly the capacity of this lossy channel, which is this very simple formula. So a note, if I put something in the middle, what I want to do, if I put something in the middle, this will be like a repeater. If an effective repeater, if I'm going to, if this repeater is going to beat, if the parties are going to beat that kind of rate, okay, if they're going to beat the PLOB bound. So if the repeater allows the parties to beat the PLOB bound, then it's an effective repeater, okay? If does not, so why to use that? It's completely useless because it means there is like, just a protocol that goes from Alice to Bob, direct transmission, which is good, okay? So you don't want to put something which is useless in the middle, okay? So you do put something which is beating the PLOB bound in such a way that no protocol based on direct communication is going to give you the same rate, okay? So you really want to beat the PLOB bound. So if you beat the PLOB bound, so you're sure that you're doing better than the optimal direct transmission protocol. And actually, this is actually in QKD what's happening. So suppose I have like, at the x-axis, the distance between Alice and Bob in kilometers, okay? So from 0 to 400. And this is the rate. No, this is number of secret bits per use of the channel. No, it's actually kind of I mean, this can become per second if you put a clock in the system, or just, I mean, just like the key rate, very general way to state a key rate in bits per use. Okay, this is the key rate, by the way. And then you have, you can see the performance. You see there's this kind of killing behavior, this kind of scaling, okay, that if you increase the distance, the rate goes down, okay? That's a command not typical on QIQT. And you see that for BBAT4, one photon BBAT4, also for continuous variables. So these protocols here, BBAT4 and CV, they're all one-way protocols on the direct channel, okay? And then you see like the PLOB bound that gives you like the ultimate limit. So these point-to-point protocols cannot go in this region, which is only accessible with effective repeaters. Now, the thing is, the interesting thing about this, okay, and also, okay, let me tell you more about this. Actually, yeah, okay, if I have like one repeater, I can go here in this region. If I want to go there even higher, you just probably need 2 or more repeaters. So each of these basically plot, if I want to go higher and higher, you need to use more repeaters, okay? And there must be more effective repeaters. So let's just focus on one repeater. So one repeater is effective if it's going to be the PLOB bound, and it cannot go in this other region. So one repeater is good. So one repeater is good if it's going to be like in this region here. And when you see MDI is not effective, okay? So you see that's MDI QIQT. So MDI is a kind of relay, so a third party in the middle, okay? Could be a repeater, an effective repeater. It is not, because the rate is too low. Actually, it's even worse than the other BBAT4 protocol and stuff like that. So it would be an effective repeater if it wasn't here, but it isn't. So that's one of the big disappointments. Because I mean, also one of the people actually devised this protocol. There were actually two papers, 2 physical letters on these protocols in 2012, and I was in one of those. But then, okay, what happened after? I mean, I published the PLOB bound. After I published the PLOB bound in 2017, the people were trying to say, okay, let's beat the bound, and the twin field was developed as a way to beat this bound, the PLOB bound. And they showed in 2019, 1 year later, that you can actually devise a different type of MDI protocol with a more clever measurement, yet a bit more difficult in the relay, which can create an effective repeater. In fact, between field, it's not in this region, which is not working very well, but for long distances, the twin field is an effective repeater. So you can actually beat the PLOB bound. So we have very long links, for the order of more than 20 kilometers, because of the PLOB bound. I mean, all the QIQT rate, the standard QIQT protocols, they are going to have like a very, very low key rate. But if you use twin field, so you can boost this, you can actually increase that beyond the PLOB bound. And it's remarkable because, I mean, this is actually a repeater, which is effective, so it's beating PLOB bound, at the same time is untrusted, so it could be operated by an eavesdropper, and there is no entanglement whatsoever involved, okay? So very 3 features within the same idea. So it's like it's effective, beating the PLOB bound, is untrusted, so it can be used by an eavesdropper, and it doesn't use entanglement, so it's feasible near term. It is actually currently implemented. So this is actually a very important tool for these near-term networks, and clearly there's a lot of research going on from this. There have been, after the twin field appeared, there were many other protocols being developed with different performances. So we see they are increasing also the rate. And all these protocols were actually somehow devised with the aim to beat the PLOB bound, okay? And so to go into this region. And potentially they can also achieve at some point the single repeater capacity, which is the best you can do with one repeater in the middle, which is this other red line here. Now, this type of products are very important. They're going to be simplified more and more over time. So what we need to do? What is actually the next step? What are the near term? Now, the near term here in this kind of development is trying to develop in other twin field like nodes, twin field like repeaters, where the key rate is better, and potentially also the protocol operation is better, okay? Because they are difficult to do now. It's a more difficult MDI. So you want to simplify the operation of these protocols, okay? I mean, what they are actually is, I mean, the operation is being simplified, I mean, by other theoretical advances. These are very, very, very strong candidates, tools for near-term quantum safe networks. So so that's the end. Some take-home messages here, right? So we started with the quantum method, which is a very complex system, an ecosystem with increasing difficulty. And I mean, from the bottom part, which is basically completely classical, almost classical, to something which is a very, I mean, based on quantum hardware, the top level. And in this system, quantum safe networks are really basic building blocks. So the very first two levels, but the QIQT is a very complex area with different level of security. For instance, particularly between standard MDI and DI, you have like increasing level of security, but decreasing types or decreasing rate, and so on. Correspondingly, these three approaches can give you three different types of repeaters and QIQT networks. And so we have like the trusted QIQT network, which is a very state of the art. We have the next step, the immediate next step, which is like this inter-LAN security with the based on MDI and twin field, and more precisely twin field repeaters. And then, okay, we have the future use case of entanglement distribution networks. Now, inter-LAN security, which is the next step, requires effective and trusted repeaters. So twin field has been the very first solution to overcome the PLOB bound. Other protocols are currently being developed and experimentally realized. Now the challenge here is to simplify these protocols in terms of operation, while keeping like I mean high rates for long distances, and potentially even better if you can increase these rates towards the I mean, the capacity for the single repeater, for the first single repeater. But generally speaking, it would be good to have like a more simpler mechanism for their operations, okay? Because I mean, as twin field by itself is a little bit more complicated because you need to be this kind of a phase synchronization, I mean, a relay, which can be highly non-trivial in, I mean, in a standard, I mean, large scale deployment, I mean, in a standard network. Okay, so that's all. Thank you very much for your attention.
Thank you, Professor Pirandola. Let's see how many questions are there in the chat box. Our participants can ask questions by unmuting themselves also. So first we'll see the questions in chat. In between, if participants want, they can unmute themselves and ask questions. Let's see what are the questions there. Questions A. First, can we achieve DI-QKD with just no signaling condition? That's what this is the first question.
Well, you
Kumar
can.
Nilesh has asked, yeah.
Well, I mean that's the way in which you can do DI-QKD clearly with I mean not signaling. I mean it's just one of the way. I mean also I want to be honest. You know that I mean DI-QKD I mean device independent is also the point different levels of security in terms of closing potential loopholes, and certainly I mean it depends of which level of how many loopholes you want to close in DI-QKD. And that's actually another level of detail that you can consider. At the end of the day, you can certainly consider like the QIQT with just no signal condition, and it's very high level of security. And at the end of and also it depends. One day, I mean, the next probably years, how much a customer from this point of view, because we talk about customers and probably want to pay for security, okay, and how many loopholes you want to close, what type of rates. That is such an option. Now the second question was the best quantum cryptography date. Well, I mean that's a good question. There's no an absolute winning technology. You really would like to have, there's now an ideal quantum crypto system. Okay, the ideal quantum crypto system will be a quantum crypto system which is able to have high rates, okay, long distances, would be able to scale very well with the number of users in a network, would have high level of security. It could be also secure with respect to side channels, but that's not the case. There are many trade-offs. So what I showed in the plot was a trade-off between rate and distance. That's one trade-off. You have a trade-off also between security and rate. Clearly, I mean, the more secure, I mean, it was a kind of implicit, you know. I mean, the more security is, usually the lower is the rate. There's also, I mean, other trade-offs in terms of security and number of users. So if the number of users could increase, the security can decrease. So if you want high level of security, probably you don't want too many users. And also between rate and number of users, distance. So there are many trade-offs. So the important thing is to understand what is like the best compromise for, I mean, for a network, for I mean, say again, a customer, whatever, and to find the best compromise, you need to choose the best compromise, depending if the rate is more important than security or vice versa, and so on. So there is no an ideal crypto system. And that question clearly, I mean, cannot be answered completely. So which protocol is efficient for long distance QKD? Which protocol is efficient for long distance QKD, continuous or discrete? Okay, so at the moment, clearly, the more robust for long distance QKD is certainly the discrete variable QKD. And there's a specific reason for that, is because, I don't know if maybe too subtle, but the point is that in discrete variable QKD, you have a photon, and which is basically a quantum of energy, okay? And then you encode the information in, for instance, the polarization, okay? And now that this photon, if this photon survives at the other end of the channel, then you make like a measurement for the polarization to drive some of the information from the polarization. Okay, so somehow the encoding is in a degrees of freedom, which is the polarization, which is different from the energy, which is the packet. Okay, in continuous variable, the encoding is in the number of packets, so it's kind of in the energy somehow. Okay, it's kind of related to the energy, so it's in the, more precisely would be in the quadratures of the field, but it's kind of similar into the number of photons, if you want, okay? And so when you have like a lossy channel, I mean, these photons are lost, and somehow you are corresponding also losing the information that you are sending. So in this key variable, it's important that as photon survive. If that photon survive, then you get the polarization information. In continuous variable, the information is somehow also in the same number of photons that you are sending. Very, very, very rough description, okay? So somehow if you go to long distances, your encoding is going to be degraded, okay? You're going to lose a lot in terms of encoding. It's not just the system. So it's more fragile. Bottom line is more fragile for long distances. But for short distances, they can give you higher rates. So if you can implement them, let's say within 20 kilometers, 15, 20 kilometers, or even very, like a local area networks, I don't know, like even with 1-2 kilometers. I mean, they may actually read a much higher rates than discrete variable, and they can do that, with the current technology. Good. Now, I have another message, which is why PLOB bound is effective for QKD. So, well, the thing probably, if I get this, I don't know if I get the answer correctly. In terms of what the PLOB bound defines an effective repeater for QKD, probably. So the PLOB bound, if I think that probably will be, because what is effective QKD, I don't know. Some of the PLOB bound tells you, with this kind of security proofs, which is based actually on, techniques based on teleportation actually, and other things like radio entanglement. So you have like a full set of techniques which come from theoretical quantum information, and basically you can find an upper bound with respect to a channel. So if I give you a channel, what is the maximum number of secret bits you can achieve over this channel? Okay, and we can compute that with this technique. And how we compute this? How we compute this is a bit clearly more complicated. So it's a very long work. But the idea is that when you have this kind of value, this upper bound is for a channel. is for a channel, okay? Right. So I don't know if I ever, okay. So that's boundary is for a channel. So it means that it's for a point-to-point implementation with a channel in the middle. So anything implemented on a channel cannot beat that bound. So if you actually breaking the channel, you're creating two channels. So potentially you can go beyond the PLOB bound for the single channel. Okay, that's the idea. So you have a PLOB bound for a single channel. If I break the channel in two, I have a different scenario. So I can go beyond, I mean, above this bound. And that's what we want to do with repeaters. So we want to break the one single channel in two channels. But then when you do that, you want to increase the performance. That's why a repeater is effective if it's beating the PLOB bound. Can repeaters affect the security of QKD? Yes, I mean, it depends how you, again, it depends on the level of security that you have. Yeah, indeed. I mean, if it is like the basic scenario is that of a trusted repeater, now, which is just a trusted node. So it's kind of a third party which is trusted. So trusted means that you are assuming, you're making an assumption that that third party is not the eavesdropper, or that party doesn't have somehow sniffers installed by an eavesdropper, or is not attacked by an eavesdropper. I mean, from the point of view of its setup. Okay, so for example, I have Alice and Bob, and I have a Charlie in the middle. So Charlie could be trusted. Okay, if you assume that it's trusted, you're making an assumption. Okay, so for example, if you make this assumption and you create this kind of trusted chain, so with this trusted part in the middle, okay, you're fine as long as the assumption can be verified. Now, if that third party somehow is attacked, I mean, the setup of that third party is attacked, so basically you're completely losing the security in the chain. Okay, so this is again, it's a kind of a game. How much I can assume with respect to the repeater. Okay, and how much I want to risk from this point of view. MDI is good in the sense that if like Charlie is performing an MDI measurement, so it's an MDI protocol, so it doesn't matter if Charlie is attacked by the eavesdropper, or it doesn't matter, okay? Because even in that case, Alice and Bob can use the system, and still they can use the system to derive a key to have security, because they have a way to also to check what's going on. And even if the relay, the repeater is operated by the eavesdropper, they are fine. So that's a high level of security. But so yes, so the repeaters, the QIQT repeaters have different levels of security. Could be trusted, they could be just untrusted in the detection, could be untrusted in both sending and receiving. And this clearly is going to affect the security of the network. And why is, okay, so we have these other questions. Why is the transmission probability down to square root of eta for single repeater system? Shouldn't the two arms be in sequence, make the effective probability square root of eta times square root of eta equal to eta again? Okay, that's a good question. Yeah. So the thing is that when you have, so you start from a fiber, okay, a channel, lossy channel with transmissivity is eta, okay. So you know that when you break down this fiber into identical segments, okay. So you have like a smaller fiber here with say, I mean, the half the length, and another here identical. So when you do that, basically the transmissivity of this fiber is square root of eta. Okay, and so you have like a square root of eta, and I put together square root of eta, I get eta again. Okay, so two fibers which are square root of eta and square root of eta together, they form a longer double fiber with transmissivity eta, right? So what's happening with the repeater? So when you have so a repeater, what does a repeater? What is an effective repeater? So an effective repeater is a repeater that, with respect to the long fiber with transmissivity eta, right, is going to give you a better result. But when you have like two small fibers like that, square root of eta, the maximum that this repeater can get is something which depends on square root of eta. What is the reason? It's because the maximum that this repeater can do is to achieve the PLOB bound for this segment and this segment. So now this segment now is as transmittivity is square root of eta, and also that one. So the best you can do in this segment is the PLOB bound, but with respect to square root of eta. And the same here is the PLOB bound with respect to square root of eta. Now the receiver, the middle relay is working well if he's able to achieve somehow the PLOB bound here and the PLOB bound here simultaneously in such a way to have the square root of eta for the entire fiber. Okay, so somehow you have a rate here which goes like square root of eta, another rate here which goes like square root of eta, and then the repeater is going to combine them to something which is still square root of eta between rise and bob. And that's the maximum thing that the repeater can do. Okay, go to that square root of eta scaling. But with MDI, even if the MDI has the potential to do square root of eta here and square root of eta there, the MDI works very badly, and when it combines the operation, achieves something which is not square root of eta from here, but something back to eta, okay, and below the PLOB bound. So that's why MDI is not working well. Twin field is able to maintain, you know, this kind of square root of eta advantage. Okay, from here to here, combining in such a way that still have some square root of eta scaling for the entire fiber. Okay. Is the maximum violation of Bell inequality necessary for and sufficient condition for is maximum violation of Bell inequality necessary and sufficient condition for the QIQT? Well, I mean, when you have this kind of, that's a very strong condition for the QIQT. In general, I mean, you need you actually need thank you. I hope that it was a good answer. Yeah, I mean, in terms of violation of Bell inequality, I mean, as long as you are able to, you know, yeah, I mean, to start violating them, to show that you actually prove no locality and violated Bell inequalities to higher levels. I mean, the highest levels you get is the highest possible way is the best possible performance at the best possible scenario. So when you have like the maximum violation of this inequality, certainly you have a situation where kind of, you know, similar to the case where Alice and Bob, they really have, you know, a maximum entangled state between them, okay? And when they have like a maximum entangled state between them, that's the ideal situation, okay? So nobody can be, novice dropper can be included in this picture. Everything is kind of decoupled from this unique, you know, entangled state situation between these two. And it's completely, everything is completely decoupled. So certainly, yes, that would be the maximum level of security you can achieve. Now, I want to be also to be clear that, I mean, even if you have like the device independent, right? And you achieve this kind of ideal scenario where you have even, I mean, a maximum entangled state between Alice and Bob. In general, I mean, it is achievable also, I mean, after distillation, okay? So you can have actually many entangled states which are degraded by the channel, but then you can distill and you can get a lower number of maximal entangled state to the level that actually they can have, you can have the maximal violation also of Bell inequalities, for instance. So when you have this kind of things, I mean, you are completely secure, okay? From the point of view of the theory. One point, but be careful, because I mean, now these kind of correlations need to be transformed into classical variables anyway. So you have to be careful, because Alice has to do a measurement on this part of entangled state. Bob has to do a measurement of this other part of entangled state. They need also to do some kind of communications between them. And from these measurements, they need to derive, right? And the outcomes. Now, again, and clearly the Bell inequalities checking and stuff like that. But I mean, the bottom line is that at the moment where they derive, you know, classical variables, you still need to have a situation where you, at that point, everything becomes classical, you know, and at that point, you know, Alice's local computer should be also shielded, you know, with respect to the classical attacks, right? So you do want that, I mean, this classical information now which is just classical bits, stored somewhere, and then there is like, I don't know, a sniffer, classical sniffer like we have today, which is getting the information about this classical part. So one very important point is that device independent QKD certainly it will be the top level, but yet the one point you need the ideal solution would be let me tell you the ideal solution would be something like device independent QKD, which is working at very high rates in such a way that you can really generate entanglement states of very high rates, something which would probably be achievable in 10 years or no. And then you can achieve this very, 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 very bright sources of correlated quantum secrets. So this kind of this quantum correlations very, very high level, and then they can all the parties are able to measure this kind of distributed states and gets there's a C correlation. So but yet even at that level you must be sure, you have to be careful that after you've done this operation, then you are again into the classical world, and then you need to protect your classical data with with what we have today. Okay. Right. So, with the classical means, with the classical cryptography. Yeah. Thank you very much. That was very nice.
Just one question, Professor Pirandola, from my side. Just wanted you talked about quantum networks. So, if there is effort going on to integrate CVQKD network and DVQKD networks, because they are very different. So, what is like? How you are going to integrate them? Yeah. Metropolitan, you talk of CVQKD, then you long distance to talk of DVQKD. How you are going to network like one metro to another metro? Suppose.
Yes, you can do that. The problem is that how you build a key management system. That's actually good. You can create like you can also have this kind of hybrid scenarios. I mentioned, there's a work in progress from this point of view as well. You have like because at the end of the day, within the somehow the setting of trusted network, that's not difficult because you may have like a small network. I don't know, like within 1 kilometers or 2 kilometers, that can work very well with CVQKD, so very high rates. And within this network, you have like a very high rate communication between the parties. And then you want to go outside with another network, okay, and which is far. So probably now CVQKD is not that mature. It's not like can be used, but it's not that mature at the moment technologically. Probably now you can use already DVQKD, and then you can use like DVQKD with this connection. You are decreasing the rate, so you're getting a bottleneck between the high rate local area network and this kind of more wide structure. Okay, now it's inevitable. In the future, probably you can also devise better CVQKD. There is not just a technological problem. There is no problem in principle in the end. You can also, it's more difficult, but you can actually increase some the clock stuff. You can have a good CVQKD also for long range. But now you have DVQKD. Okay, so what you do is basically at the interface you need to manage the key in such a way that you should have a very good key management system that is going to swap the keys that you generate locally with the CVQKD with the keys that you generate somehow in the middle between the two LANs with the discrete variable QKD. And then you can use stuff like the one-time pad to do this kind of swapping anyway. So you can actually swap keys coming from different protocols, and they may come from continuous variable protocols or discrete variable protocols. It doesn't matter too much. You can use one-time pad. You can use the advanced encryption standard or stuff like that. That's really possible. Now, actually, seeing Giulio here, Kiribella, he's probably the next speaker, right?
Yeah, he's the next speaker. Yeah. So thank you very much. Yeah, he's waiting. Yeah. So we should invite him now. Yeah. Okay. Thanks a lot.
Okay. Thank you very much.
Yeah.